Hello everyone, welcome back to Networks class. Last time in class we went over homework 2, which was a homework on using shortest path models. So now you should all know about things like time layering, for example. And then at the end of class we talked about the new homework assignment, homework 3.1, where we'll be helping the Arizona State Police try to capture an escaping drug lord. And the plan for today is to go back to the lecture that we had before last time, where we discussed Bender's decomposition for shortest path interdiction. So at that point, we just got to discuss the basic algorithm to do this, but we didn't get to see an example. So the plan for today is to go back and do an example of Bender's decomposition. And then when we're done with this example, we'll go on to our next network problem, which is the maximum flow problem. So we'll be able to just get a start on that today. So let's go back and review a little bit about how Bender's decomposition worked, and then do an example on a particular graph. So roughly, this is what the pseudocode for Bender's decomposition looks like. So we had this big LP, the full master. The full master looks something like this. We wanted to maximize over theta and x. We wanted to get theta be as big as possible, and theta had to be less than or equal to the sum over ij in a path, the cij plus dij xij. And this was for all paths from S to T, P. But the problem with the full master was that it had too many constraints, so too many paths, and we couldn't do that. And so the idea was to kind of generate these one at a time. So that's where this idea of a partial master came from. And the idea in Bender's decomposition is that we're going to start the partial master with just a single constraint. And that constraint is going to correspond to just to the uninterdicted shortest path, which is the path that the shortest path player would take if we don't attack any arcs. And then we're going to maintain an upper and lower bound on the optimal objective function value of the full master. The upper bound is going to start out at infinity, but we can set the lower bound to be equal to the shortest path length of the uninterdicted shortest path, because regardless of what we do, the shortest path player has to do at least this much work to get through the graph. So that's why that's a reasonable lower bound. So then the algorithm proceeds in this loop. So we're going to keep doing the loop while the upper bound is far away from the lower bound. And what far away means really just comes from our definition of how suboptimal a solution we're willing to accept. So you could wait until these two are equal, in which case you'd have an optimal solution, or you could wait until some other time, in which case you'd get perhaps a suboptimal solution. So then the loop proceeds as follows. We're going to go in and solve the partial master, and that's going to get us a solution theta hat x hat. And the theta hat that we get out of the partial master, that gives us an upper bound to the optimal function value of the full master, because the partial master is a relaxation of the full master. And so whatever solution that we get out of the partial master must be an upper bound to the full master. Then we're going to go and solve for the best response shortest path if we happen to use the attack plan x hat that came out of the partial master. So let's call that path P and its length L. If it turned out that theta hat is less than or equal to L, then we're done, because the solution to this relaxation is feasible in the full master. So that means that it must be optimal. But otherwise, we're going to set the lower bound equal to the maximum of whatever lower bound we had before in L, and add P to the partial master. So right here we're adding a new constraint to the partial master. But let's discuss a couple of things. So first, why is L a lower bound? It's a lower bound because we know that if we follow attack plan x hat, we can force the shortest path player to spend at least L work to get from S to T. So that means that regardless of what we do, at least we know that this plan guarantees us that we can force him to do this much work. So that's why it's a lower bound. We could potentially do better than that, but we can at least achieve L. So the other thing I wanted to point out is the difference in how we're setting the bounds. So you can see that with the lower bound here, we're being careful to say that the new lower bound is the maximum of the old lower bound and L. While for the upper bound, we're just always setting the upper bound equal to theta hat. So why is that? It's because if you look at the solutions that come out of the partial master over multiple iterations here, they kind of they give us better and better bounds. So let's think why that is. So here's a bit of a picture. So imagine that this is the optimal objective for the full master. So it's right here. We don't know what it is, but we know that when we go and solve the partial master the first time, that gives us some upper bound. So this is upper bound from solving the partial master the first time. So that would be the first time in the loop we get some upper bound. But at the end of this loop, what we're going to do is we're going to add another constraint to the partial master. So the next time we go and solve the partial master, since we've made it more constrained, the second time through, it can only give us possibly a lower upper bound. So improved upper bound second time through. And that's because the second time through, the partial master is more constrained. The third time, it's going to be more constrained, and so forth. So these upper bounds are monotonically decreasing, which is why we don't have to be careful here. We can just say that the upper bound is equal to whatever comes out of the partial master. So the same is true not for these. The same is not true for these lower bounds. They're not monotonic. So and we'll see that in the example in just a little bit. Okay, so that's the basic overview of Bender's decomposition. Now let's take a look at a specific graph and try to execute this to see how it would work. So here's a specific graph. So we have S, 0, 1, 2, 3, 4, 5, and T. And let's say the graph looks like this. And we're going to put some costs on these edges. So this edge has cost 5. This one has cost 5, 0 and 0 here. Let's say 3, 1 and 3 here, and 0, 0 and 0. So let's also say, say the Dij is infinity for all edges. So what this means is that if we attack a particular arc, its cost all of a sudden becomes infinity. So that's the equivalent of essentially removing the arc from the graph. So we're saying our attacks here are very powerful because they change edge's length to infinity. So let's also say that we have 2 attacks total. And so our goal is to try to figure out the best place to spend these 2 attacks to cause the shortest path player to have the maximum amount of effort to move from S to T. And really, you can just kind of see visually what the right answer should be over here. The right answer is to kind of take out maybe S0 and S1, some kind of combination that takes off this top path between S and 2 and this bottom path between S and 2. So if I do that kind of a combination, it would totally separate S from T. But you know, a computer wouldn't be able to do this just by looking at the graph. So let's see how Bender's decomposition would deal with this. So let's start here our partial master. So it looks like this. So it would be maximize over theta and x. So we're trying to maximize theta. And at the beginning, this partial master is going to have only one constraint that corresponds to the shortest path. So the shortest path from S to T here is S to 1 to 2 to 4 to T. So let's write that down. So that's the S to 1 to 2 to 4 to T. So that's the path that we're going to write the constraint from. And the constraints, if you recall, basically say Cij plus Dij times Xij. So let's write that down for this path. So for the first edge here, its cost would be 5, plus the Dij for the edge, which was infinity, times the x for the edge, which is xs1. So that was this first edge. So let's do the next edge, which is plus 0 plus infinity times x12. So that was these first two edges. Let's do the next edge. So that's plus 1 plus infinity times x24 plus 0 plus infinity times x4t. So that's the single path constraint that we have in the partial master. And of course, we have the resource constraints on the x's. So we have a constraint that looks like the sum over all ij of xij is less than or equal to 2. And that corresponds to the fact that we have just 2 attacks available. So that's what the partial master looks like from the beginning. So let's also write down what our lower and upper bounds are. So we have to maintain these lower and upper bounds. So at the beginning, the upper bound is going to be equal to infinity. And the initial lower bound is just going to be the shortest path length, because even without attacking, the shortest path player has to do this amount of work. So our lower bound here gets initialized to 6. So that's all the stuff that we have to do before we get to the loop. So now we're at the beginning of the loop of benders, which basically says keep doing the loop until these two upper and lower bounds get very close to each other. So they're still not close to each other. So that means we have to go in and solve this partial master. So in reality, you would have a computer go off and solve this integer program. So it's an integer program because the xij's have to be either 0 or 1, because we have to decide whether we attack this arc or not. But for a small example like this, we can just do this solution in our head. So we're trying to make the theta be as big as possible. And the thing that's making us, or the thing that's stopping us from making theta be big is this constraint right here. So the only way that we can make theta be big is if we make this right-hand side over here be very big. And the way that we can make this right-hand side be big is if we take one of these x's and make it equal to 1, right? So for example, if we make x4t be 1, this right-hand side is going to be infinity, which allows us to make theta be equal to infinity as well, which would then be an optimal solution to this partial master, because you can't make theta any bigger than infinity. So that tells us that the solution that we get out of here is theta hat is infinity, and let's say x hat 4t is equal to 1, and other x's are 0. So that's the specific solution that we get out of the partial master. So the next thing that we would do is go and update the upper bound with this new upper bound that we got from the partial master. But the new upper bound in our case is infinity, and the old one was also infinity, so there weren't any updates there. So the next thing to do is to try to figure out what's the best response, shortest path plan if somebody uses this particular attack plan. So this particular attack plan says that we would go to edge 4t and we would take that edge out. So then the best response plan for the shortest path player would be something like go to S to 1 to 2 to 5 to T. So the best response is S to 1 to 2 to 5 to T. And of course, you can see in this particular graph there's a different best response. We could have just said S to 0 to 2 to 3 to T. That's just as good a path. Or S to 1 to 2 to 3 to T. That would be just as good a path. And you can get any one of these best responses out as long as it's some best response. But let's say that we get this particular best response out, and its length is going to be 8, because that's the path length of this path. So now we have to see if this 8 is better than the previous lower bound that we had. So it is better, so we have to update our lower bound. So it used to be 6, and now it's 8. And the reason we updated it is because we know for a fact at this point, even if we stop the computation right here, we know for a fact that if we go and we attack edge for T, then that's going to force the shortest path player to spend 8 effort. So even if we stop, I know a way of guaranteeing at least 8 effort from the shortest path player, and that's where the lower bound comes from. So we updated the lower bound, and the next thing to do is we have to add a constraint to the partial master. So the new constraint that we're going to add corresponds to this path. So let's write that down. So that would be 5 plus infinity times xs1 plus 0 times infinity times x12. So I'm going to just not write in the 0. So it's just going to be infinity times x12 plus 3 plus infinity times x25 plus 0 plus infinity times x5t. So that would be the new constraint that we add to the partial master. So that completes our first time through the loop. And the next time that we're through the loop, the upper bound and lower bounds are still far away from each other. But when we go to solve the partial master, we're still trying to maximize theta, but now there's two things that are stopping theta from being big. So that's this first constraint here and this second constraint. So how can we get theta to be very big? Well, we have to get both of these right-hand sides to be big. And so let's think about that for a little bit here. How can we do that? Well, we can do that by setting x12 to be 1. So if I set x12 to be 1, then both of these right-hand sides are going to be infinity, which lets me set theta to infinity. So a solution that I could get out is something like theta hat is infinity, then x12 is 1, and other x's are 0. Okay, so let's see if that updated my upper bound. So the x hat that I got out was infinity, and my original upper bound was infinity, so no updates there. So the best response, shortest path plan, we would compute in the following way. So now we're looking for the best response to just this attack plan. So in this attack plan, we're attacking arc 1, 2, but we're not attacking any other arc. So this arc that used to be attacked previously from 4t, it's no longer attacked. And the only thing that we're attacking is arc 1, 2, because we want to figure out the best response to just this particular attack plan right there. So the best response here would be something like S024T. And the length for that particular path would be 6. So now let's see if we're updating the lower bound. So the new lower bound that we got is 6, and the old one was 8. So we don't do an update over there. So what that means is that this attack plan was actually worse than the previous one that we had. So the previous one guaranteed us that the shortest path player would have to do 8 work, but this particular plan only guarantees us that he has to do 6 work. So that's why we didn't update the lower bound. But we are going to add a constraint to the partial master. And the constraint corresponds to this path, S024T. So let's do that. So that would be 5 plus infinity times XS0 plus 0 plus infinity times X02 plus 1 plus infinity times X24, and then plus infinity times X4T. So that completes our second time through the Bender's loop. And now the third time through the Bender's loop, there's actually 3 constraints that are stopping us from making theta be too big. So the 3 constraints are for this original path, for this first path that we added, and for this third path that we added. So it's these 3 constraints that are stopping us from making theta big. So if we wanted to make theta as big as possible, we have to worry now about 3 right-hand sides and how to make them big. Now, of course, in reality, a computer is going to solve this, but this is still small enough that we can just do it in our head. So let's think about it for a second. If we set x4t to be equal to 1, that makes only 2 of these right-hand sides be infinity, but this third one is not infinity. If we set something like xs1 be equal to 1, then it makes these first 2 be infinities, but not this bottom one. And so after thinking about this for a little bit, you'll see that we really have to, at this point, attack 2 edges to try to make all 3 of these be right-hand sides be big. So let's say that the solution we get out is that theta hat is infinity, which we can achieve by attacking xs0. So that sets this right-hand side to infinity. Then xs1, which sets the other 2 right-hand sides. So that's the xs1 here and here. And other x's are 0. So then let's think about the best response. So again, the best response is just to the attack plan that we currently have. And the attack plan says attack xs0 and xs1. So if we attack those 2 edges, the best response here is that, well, there is no longer a path from S to T. So no path, which means that the length is infinity. So since the length is infinity, that's a lot better than our lower bound of 8. So 8 gets replaced with an infinity. And you can see that, that at this point we're done. There's a couple of ways to see that. So first is that the upper bound is less than or equal to what we had previously here, which was the infinity. And so now you have a relaxation to the you have a solution to the relaxation, a solution to the partial master that's also feasible in the full master. Or another way to see it is just the upper and lower bounds here are now the same. So we're at the end of the loop. And you can see that we could have made a mistake on this last one. So instead of saying xs0 and xs1, we could have, for example, done x4t and x5t. So if we did x4t and x5t, it would have set this to infinity, these 2 to infinity, and x5t would have set this middle one to infinity, which would have made us generate a new path. So let's just think about this for a second and how it would look. So if we attacked these 2, it would have generated a path something like this up here. And then the next time through, we would have had to satisfy 4 equations. And to satisfy those 4 equations, there would be no way to do it by attacking these arcs over here, because we only have 2 attacks total. So you'd have to concentrate your effort on this first part of the graph right there. So it may have taken us a few more iterations, but we would have gotten the same kind of optimal answer here. So that's the basic idea of Bender's decomposition and how it works. But I encourage you to just repeat this example, but repeat it by allowing yourself only one attack. So instead of 2 attacks, let's say that you only have 1. And you'll see that if you run that, you're, again, only a few iterations, you're going to get to the right answer. But what's going to happen is your upper bound here is going to start decreasing, because eventually you're going to get a few constraints, maybe 2 or 3 of them, such that you can't make all of the right-hand sides be infinities. So once you can't make all of the right-hand sides be infinities, then this upper bound is going to come down from infinity to be something else. So try running this with just having 2 attacks. So before we move on from Benders, there's a few other things I'd like to emphasize. So the first thing I want to emphasize is sort of one of the benefits of Benders, which is that Benders lets us get back to using Dijkstra's to solve shortest path. Whereas the mixed integer program that we had written previously for shortest path interdiction uses an LP to solve shortest path. So let's see exactly what I mean by Benders allows us to use Dijkstra's. If you go back and look at the Benders pseudocode, one of our steps here was to solve for the best response under a particular attack plan. But we can get this best response in any way possible. So in particular, right here, we could be using Dijkstra to generate this best response. It doesn't have to be an LP. It doesn't have to be anything. As long as we know what the best response shortest path is. And that allows us to stick in our special purpose, super fast shortest path algorithm into the computation of this shortest path interdiction problem. So that's a big benefit of Bender's decomposition. So another thing that I wanted to point out about Bender's is that, or this is actually true for all shortest path interdiction problems, is that in terms of taking out an arc entirely, the way that we did that in this example is by saying that the Dij is equal to infinity. But computationally, it's quite difficult to actually put in infinity into a computer. So what can we do instead of doing infinities? So intuitively, if you make the penalty big enough, it's going to act like an infinity. So let's see how big of a penalty is sufficient so that it acts like an infinity. So imagine that we have a graph here. So this is a graph G, and somebody's solving a shortest path from S to T. And the question is, how many edges could the shortest path have? So in maximum, since a path has to not repeat any node, in maximum there could be n nodes total. And if there are n nodes, that means that the number of edges between them could at most be n minus 1. So the maximum number of edges that any path can have is n minus 1 edges right here. So so the length of every path from S to T must be less than or equal to n times what we'll call Cmax, where Cmax is equal to the maximum over all edges ij of the cost of the edge. So the only thing that's getting said over here is the following. A path has to have n minus 1 edges. So its total length has to be less than or equal to n times Cmax. And in fact, it has to be strictly less than n times Cmax. And so if I have a particular edge over here, and I make this edge's cost be n times Cmax, then the shortest path player would prefer to walk anywhere else in the graph before taking this one edge, because just taking that one edge is as expensive as walking across a path that involves the maximum number of edges elsewhere in the graph. So computationally, instead of using infinities, we can just use this quantity n times Cmax for our penalties, and it acts like an infinity because it forces the shortest path player to walk around the edges that are n times Cmax long. So one final comment about benders before we leave it, which is just this, I want to remind you of this interpretation that we can have of benders, which is you can think of it as a game between two players. So it's the interdictor versus the operator. And the operator is kind of solving shortest paths. For our particular example, he's solving shortest paths. And you can think of the interdictor as basically corresponding to the partial master. And the operator is kind of corresponding to that best response, shortest path. And the basic idea here is that the interdictor comes up with an attack plan. And then the operator shows his best response. But then the next time that the interdictor comes up with an attack plan, he's going to remember all of the best response plans that he's seen from the operator. So next time, the interdictor creates an attack plan. He remembers all the plans the operator has shown. And this remembering in terms of Bender's decomposition is happening because of the extra constraints that are getting placed inside of the partial master. So every time that the partial master computes an attack plan, it's taking into account all of the operator plans that the operator has shown thus far. So you can think of the interdictor as kind of building up a portfolio of the available plans that the operator has, and then considering the entirety of the portfolio that he's built up to come up with his next attack strategy. And then once he produces that attack strategy, he shows it to the operator, and the operator says, okay, well, if you do that attack strategy, I'm going to have this response plan, which maybe is not in your portfolio. And if it's not in the portfolio, then the interdictor takes that plan, adds it to the portfolio, and recomputes a new attack plan. So that's probably a good or a reasonable way of having an interpretation of what Benders is doing just intuitively. So that basically concludes our discussion of Benders. decomposition. And Bender's decomposition tends to work a lot better than these mixed integer programs. Again, because the mixed integer programs don't get us a lot of benefit in terms of branch and bound. So now we're ready to move on to our next network problem that we're going to study in class, which is called the maximum flow problem. In the max flow problem, we're given two nodes, S and T. And our goal is to ship as much material from S to T as possible. But we also have capacities on each edge. And these capacities tell us the maximum amount of material that we could ship through the edge. So typically, we're going to designate these capacities with the letter Uij. And U just comes from upper bound, because that's the maximum amount of material you could move across the edge. So quite usually, S is called the source. And T is called the sink. That's because material is coming out of S and it's going into T. So let's just do a brief example of maximum flow, something that you could just solve by looking at it to get an idea of how this problem works. So here's S, here's T. We have a simple graph. So let's say the capacity here is 3, the capacity here is 10, 15 down here, and 2 over here. So now somebody comes along and asks us, how much material can you ship from S to T? The total amount that we can ship from S to T in this graph is 5, because we can ship 3 on this northern route and 2 on this southern route. So total 5 from S to T. And we're already familiar with how to formulate this problem as a linear program. So we saw this in our overview of network problems. So the linear program for this looked like this. It was maximize over y and v. We want to get v to be as big as possible. And everything coming into S, everything going out of S has to be equal to minus v. Everything going into T, everything going out of T has to be equal to V. And then for all other nodes, whatever comes in has to be equal to whatever comes out. And finally, we want to make sure that the number of trucks going across arc ij doesn't violate this capacity, and that it's bigger than or equal to 0. So that was the basic linear program for the max flow problem. But let's get some more intuition about how this problem behaves. So the first thing that's going to happen is we'll assume if edge ij is in G, then so is edge ji. So in other words, if I have two nodes here, I and j, and originally we just had one edge from I to j with capacity 5, the reason it's okay to assume that the other edge is there is because we could just place an edge in the other direction that has 0 capacity. So this is the same as above. So that's why we'll assume that both directions of the edges are present. Okay, so now imagine I have two nodes here, I and j. And on this top arc from I to j, I have a capacity of 8. And currently we're sending 8 trucks on that edge. And from j to I, we have a capacity of 5. And currently we're sending three trucks from j to I. So every day, we're sending 8 trucks from I to j and 3 trucks back from j to I. So that means that net, we're sending 5 trucks from I to j. But if you look at this, this arc, it looks like we cannot increase the total flow that's going from I to j. But the maximum net flow from I to j is actually 8. So we could potentially have 8 trucks total be moving from I to j every day. And the way that we would do that is by basically backing off on these 3 trucks, by telling these 3 trucks, hey, don't be coming back from j to I, just stay at j. And if we get those 3 trucks to stay there, then every day in total, we'd be sending 8 trucks from I to j instead of 5. So that motivates something called residual capacity. That's basically going to tell us the total amount that we can change the net flow between 2 nodes. So let's get a few definitions to clarify all of this. So the first definition here is that we say a vector y is a flow if it's feasible in the max flow LP. Our next definition is that given a flow y on a graph G with capacities U, the residual capacity of arc ij is, we're going to denote that as Rij. It stands for residual capacity of arc ij. That's going to be equal to Uij minus Yij plus Yji. And what this denotes is, this means the amount of net flow we can increase from I to j, or the total increase in the net flow that we can achieve from I to j. So let's see where this definition is coming from. So if you look over here, back in our picture here, if we wanted to increase the net flow from I to j, we could do it in 2 ways. One way is to kind of get more trucks on this edge from I to j. We could be sending more stuff over here. But how much more we could send basically gets limited by how much capacity we have left. So that would be some kind of U minus Y, because that's the capacity that we're not using. Another thing we could do is that we could be backing off on these trucks that are going the other way. And so it's exactly those 2 terms that show up in the residual capacity definition. So this first subtraction right here corresponds to the capacity that we're not currently using. So that's the total capacity minus whatever we're using now. And to that, we're going to add these trucks that are going back in the opposite direction, because we could possibly be backing off on those. So that's where the definition of residual capacity comes from. Our next definition is the following. So for a graph G and a flow Y, the residual network G of Y has the same marks as G, but capacities Rij instead of Uij. So it's going to have these residual capacities as capacities on it. So let's do an example to make sure we understand how this works. So here's a graph. On this edge from S to A, let's say that we have a capacity of 4, and currently we're sending 3 trucks across that edge. Let's say from A to T, we have a capacity of 5, and currently we're sending 5 trucks across that edge. From B to A, let's say that currently we're sending 2 trucks, and the capacity is 3. From B to T, the capacity, let's say, is 1, and currently we're sending 0. From S to B, currently we're sending 2 trucks, and the capacity is 2. So the first question that we could ask is somebody comes along and gives you this particular trucking plan. So one question is, are the Y's over here a flow? So what we'd have to check is that they're feasible in the max flow LP. And to do that check, first we have to make sure that we're not violating any of the capacities. So we have to make sure that all of these Y's are less than their corresponding capacities, which in this particular example they are. But the other thing we have to check is that for every node other than S and T, whatever comes into the node goes out of the node. So let's do that. So for node A, there's 5 trucks coming in total, so 3 from this edge and 2 from this edge. And there are 5 trucks going out, so everything matches up over there. For node B, there are 2 trucks coming in total, and there are 2 trucks going out. So everything matches up over there. And the final thing we have to check is that whatever comes out of S has to eventually end up in T. So the total amount of trucks coming out of S are 5, and there are 5 trucks going into T. And so, yeah, the Y's over here create a flow. So now let's draw the residual network. So the residual network. So that's S, A, B, and T. Okay, so what's the residual capacity of going from S to A? Well, we could just apply the formula. So that would be U minus Y plus the Y going backwards. So U minus Y here is 1, and the Y going backwards is 0. So the answer here is 1. Or you can think about it also intuitively. The amount of net flow we can move from S to A is just 1 extra 1, because that's the amount of capacity that we're not using. So what about the other way, from A to S? How much, what's the residual capacity on that? Well, it looks like this edge from A to S is not there, but that's because we're just going to have the convention that any arc with 0 capacity we're just not going to draw in. Really, there's an arc over here that's pointing back that has 0 capacity and 0 flow on it. So you can just apply the formula. So it has 0 capacity and 0 flow, so this first part is 0. And the second part, we could back off on the 3 trucks that are going from S to A. So the residual capacity on this arc is actually 3. So another way you can think about it is I could increase the net flow from A to S by backing off on the 3 trucks that I'm sending. So you can apply similar reasoning to the various other edges. So the residual capacity from A to T is 0 because there's nothing more we can do to increase the net flow this way. So since it's 0, we're not going to draw it in. But the residual capacity for this arc pointing back is actually 5 because we could back off on the 5 trucks that are going from A to T. The residual capacity of going from B to T is 1, and the residual capacity for going back is 0 because there aren't any trucks to back off of on this arc. So from B to A, the residual capacity is 1 because I could potentially get one more truck to go up here. And from A to B, the residual capacity is 2 because I could potentially back off on the 2 trucks that are going across that edge. And so the final edge here from S to B has 0 residual capacity, but from B to S has a residual capacity of 2. So let's see why we're at all talking about these residual capacity networks. So if somebody comes to you and says, okay, this is my trucking plan from S to T, and I'd like you to help me see if I can get any more trucks to be moving from S to T. So if you look at this without looking at the residual, you might say the following. Well, I can't send any more trucks down here to B because this arc is already maxed out. So my only option is to send more trucks out of the top here. But if I send a truck out of the top, I can't send it all the way to T because this arc here is maxed out. So just by looking at this, you might say, okay, there's no other way to send a truck from S to T. But that's actually not the case. So let's look at the residual network. In the residual network, there is a path from S to T. So here it is. I could go S to A to B, and B to T. So on this path, there's a capacity of 1, which kind of tells me I could send 1 extra truck on there. But what does that actually mean? So in particular, what does this edge right here mean, the edge from A to B? Well, that edge corresponds to backing off on sending one of these 2 trucks from B to A. So currently I'm sending 2, and over here, if I back off on 1, I'd be only sending 1 truck from B to A. So I could increase the flow on this path, which means send 1 trucks from S to A, stop sending one of these trucks from B to A, and have this truck take over its route. And this truck that we stopped from going from B to A, have it go from B to T instead. So in this way, the residual network is actually giving us the possible changes in net flow between the nodes, whereas the original network is not really representing these possible changes in net flow in a very nice way. Next time, we're going to see a lot more about residual networks, and we're going to get a lot more intuition about max flow problems. But for right now, let's just end it here. So thanks a lot for listening, and I'll see you all next time.